doing, but I'm not going to go as much into detail about the kind of various different algorithms and techniques that we're using than perhaps some of the previous talks have. I'm going to try to show you a bit more about what we do with this and why we think this is a good way of doing the kind of problems that we would like to do. And I've given my talk a new title that I haven't used before. And that's basically what we aim to do, is to carry out computations at what is called the edge of chaos. And the edge of chaos is typically defined as the kind of razor-thin part between smooth functions and those that are chaotic. There is a region in between where basically the system is neither chaotic nor smooth. And of course, what we like to do is explore that region, because that's where interesting solutions arise. That's where there is some computational capacity in the system, meaning it can store, it can retrieve, it can perform computations, but it's not chaotic, so it doesn't become completely unpredictable. And that's, of course, exactly where all the pattern formation, all the complex physics and biology and economics, for that case, happen. And so the question is whether we can somehow move towards that regime where this interesting physics happens. I'm going to try to explain to you today how we are approaching this, and then show you some of the results that we have obtained, mainly in the area of computational fluid dynamics, where, of course, this kind of question of turbulence and how you actually deal with turbulence is an important one. So the basic setup that we're always looking at is, sorry?
Maybe you can go to full screen.
Well, yeah, let me just see. I did go to full screen before, but now, right. Okay, so the setup that we're using in most cases is what I show here. So we're basically looking at hybrid optimization problems, or hybrid variational computation, where we have a feedback loop between a quantum system. This doesn't seem to work. Where we have a feedback. Oh, that's good, thanks. Oh, it's that. So we have a feedback loop between a classical HPC computer and a quantum computer. And the idea is to iteratively optimize a cost function. And that cost function then allows us to retrieve the solution of the problem. And so how this works in principle is that we do have a classical computer that works out variational parameters. Those variational parameters set the parameters, the kind of gate angles and so on, of the quantum computing circuits that are being run. From that, we measure a cost function, feed that back into the classical computer, and iterate this until we get to the solution. And of course, we do so by just basically iterating until the cost function remains constant. And we hope that we have received useful solution that minimizes the cost function. This actually goes back to a paper in 2014 by Beruzzo and others, which introduced this variational quantum computation idea. But of course, for the types of problems that are most interesting, this is not going to be enough to just solve this kind of problems for linear problems. So what we did in 2020 was to extend this idea, this basic idea, to the solution of nonlinear problems, where we basically just make use of the fact that all the quantum circuits that we have are quantum circuits that are parameterized by known classical parameters. So this means that we can generate as many copies of the quantum state as we wish. We are not limited by the no-cloning theorem in quantum physics, and hence we can actually generate multiple copies and then produce nonlinear types of cost functions. And in particular, we're looking at the quantum part of the setup that I've just shown that looks like this and can be divided into three parts. There is this part number one, so shown in red here. That's what produces the trial function. So this is basically where the variational parameters determine the circuits that are in here in these red boxes, and those circuits then generate the functions that we use as trial functions that should in the end become good solutions to our problem. And then we have here what we call a quantum nonlinear processing unit that takes all of these different trial functions and works out the cost function from those. So basically that can multiply different of those functions together, add them, and so on. And all of this happens in a controlled fashion. It's controlled by an ancilla qubit, and all that we need to do in order to read out the cost function is the end to measure the ancilla qubit, and the ancilla qubit may either point up on the Bloch sphere or point down on the Bloch sphere, or be somewhere in between. And the optimum of the cost function will be obtained if the qubit points down to the south pole of the Bloch function, so of the Bloch sphere. So basically, we have to do only a single qubit measurement, and since we only have to do a single qubit measurement, the overhead from kind of running multiple shots is relatively small and can, in principle, be achieved by just running it kind of a couple hundred times in parallel. And what we can show then is that any cost function of this type here can be realized. So we can have any kind of function as a trial function, fj here, apply any linear differential operator to it, produce a product of such functions, and then what is not shown here, integrate over that whole function. And this setup carries out the integration. So what we measure up here is this cost function integrated over all space. Now, this has multiple potential applications. Some of them we studied already, some of them not yet. So one of the most obvious is, of course, to use this for doing quantum simulations and to extend what one usually does to nonlinear mean field theories and other such kind of theories that are not dealing with the exact many-body Hamiltonian. But what we've mostly been doing in the recent years is to use this for fluid flows and combustion physics. So those are the two applications that I'm going to show you. And what we would like to do is what we call quantum industrial design. So that's the kind of AI-generated thing of what we're going to do. And we won't be able to talk about that yet. We don't have anything. And of course, plasma physics is another kind of application that would be extremely useful to explore in more detail. Now, how do tensor networks come into this? So the basic idea that we started out from was that we have been using tensor networks for many, many years to describe many-body quantum systems. And that's been extremely successful. So all of these different types of quantum networks that you've heard about in this workshop extensively are used for describing these types of systems. Now, we can also then, and that's what we investigated first, we can also take those types of problems that we would like to solve, and in this case I show a Taylor-Green vortex from fluid dynamics, and see whether we can describe the physics that happens there using tensor networks too. And it turns out that this is indeed possible. And then, of course, it's quite easy to say, well, what we do now is we don't just use these tensor networks to describe what goes on in a quantum system, but we turn this here around, and we basically start from here, find a description of the fluid dynamics problem in terms of tensor network, then use that tensor network to program the quantum computer. And so essentially, for us, tensor networks are a programming paradigm for quantum computers that allow us to encode efficiently the types of problems that we'd like to solve. Now, something I don't have to say much about here is that, of course, these child functions that we are going to need will be functions like spatial functions, pressure fields, fluid flow, velocities, other types of quantities like temperature, entropy, and so on, entropy, as a function of space. And we do this in the standard amplitude encoding method. And the standard amplitude encoding method has, of course, the big advantage that compared to classical encodings in grids, saves you an exponential amount of memory. And also that this is, of course, highly compatible with tensor networks. So this is one of the main reasons that tensor networks are extremely useful for as a programming paradigm here, because they inherently preserve this quantum advantage of only needing a kind of logarithmically small number of qubits. And so that's what we use. Now, the kind of notion of the edge of chaos that I would like to talk a bit about comes in when we then look at how difficult and how much effort is it to actually create some of those trial states. So we would like to have the solution or ansatz for our solution encoded in a quantum circuit. So we have a quantum circuit shown here with some arbitrary SU2 gates that basically always act on neighboring qubits. And you could equally say, well, this could also be MPOs that act on neighboring qubits in this Brickley structure. And then we can ask the question, how does information spread through this system? And when we look at, for instance, a kind of angle that determines what the action on that qubit here is at the initial layer of this circuit, then that parameter that we choose here, the information of that parameter will spread out in this light cone fashion due to this Lieb-Robinson bound linearly throughout the circuit. And if we then look at what happens here at this point, well, equally, there will be a light cone spreading out and light cone spreading out from each of these initial layers of the circuit. As soon as these layers, as these light cones start to overlap, parameters from this point and from that point here will affect the physics or the kind of state at this place here that we get here. And if we go even further, then basically all of the parameters that we've chosen here at the beginning will have an effect on the state that we get back there at the end of the circuit. And now this is a tool that is used in quantum information to do scrambling. And it's a kind of very important notion. If, for instance, one of the questions whether kind of black holes are compatible with quantum physics is whether scrambling happens fast enough. And what that is scrambling essentially means is that back here, we cannot distinguish the from the state that we get back there, which of these circuits was used here. So at the back here, the start of this circuit looks like it was a totally arbitrary, random circuit. And that, of course, means that all that a change in these circuits does is just to produce noise there. So that means that we don't really need to actually change parameters in the circuit at the beginning here if we have a depth that is so large that these light cones all overlap. All that we'll do is just create noise. And that means that this type of network or this type of circuit is no longer trainable. And that means we would like to avoid that. We don't need to do this. We don't need to have a circuit that is deep so that it only does scramble the state anymore, because noise is something we actually would like to avoid. We can just average over, or we would like to just add explicitly if we want to, but we certainly don't want to spend our time training a noisy state. And of course, that is one reason that leads to barren plateaus and makes the whole thing untrainable. And the question is now, what do we do in order to avoid this from happening? So how do we avoid scrambling? So it's basically the opposite question to what other people ask when you actually ask, why do we want scrambling? For instance, for encoding and for cryptography, scrambling is a very useful tool, but here we would like to avoid it. And one quantitative figure of merit that tells you how scrambled a state is this so-called I3, the tripartite entanglement entropy. And that basically tells us, I've listed it down here, but I'm not going to go into the details, that tells us how much mutual information is shared between A and B and between A and C, minus the amount of information shared between A and B and C combined. And when that becomes negative, then that means that the mutual information between A and B and C is non-redundantly encoded in B and C. So the whole B and C is necessary in order to learn about the state in A. And if that happens, if the information is spread over the whole system, then that's a sign of chaos, that's a sign of scrambling, and that's what we would like to avoid. And when we now look at this circuit and how it evolves in time, we see that this I3, this measure of how scrambled a state is, starts out at 0, so it's not scrambled at all, until basically these different light cones start overlapping. And then, and this is shown for different sizes of the or width of these quantum registers here, then this I3 goes down and becomes negative, and here takes on its minimum value when these different light cones all start to fully overlap. And so that means that we here have now a region where the system is smooth, and this I3 is in this case 0. So that's something that is very easy to describe, and basically everything is smooth and well behaved. Then there is a region where this kind of scrambling starts to set in. The I3 goes down, becomes negative, and then it stays at this value of -1, is fully scrambled, and all that happens is only chaos. And so what we would like to do now is we would like to carry out the computations in this region here. This region is easy. You can just use whatever algorithm you have. You don't need any kind of fancy quantum system or tensor network algorithm. This region is fully chaotic. There's also not much point in the numerics here, but this is the region where we think that all of the interesting physics happens. Now, of course, the question that goes with this now is how big, how wide does this quantum register need to be? How many qubits do we need in order to have a kind of faithful and kind of well-suited trial state to represent our solution? Because there are two things. First of all, it's of course the number of qubits that we need in order to run our computation. But secondly, the wider this circuit is, the longer we take until scrambling starts to happen. And so what we've investigated, and that's one of the places where we use tensor networks, and in this case a tensor train, is to just look at a simple sine function and look at how this sine function actually behaves if we write it into this quantum register. So for the sine function, of course, we can straightforwardly write down all of the kind of different tensors that appear here. And what we then do is we take the limit of n, the number of qubits going to infinity, and we look at the reduced density operators for the individual qubits. And what we find for these reduced density operators, well, it's given here, not a very interesting expression, but what is important here is that as we move to a q that is larger than some critical q, so the q here is basically the number of the qubit that we have. Yes? Yes. So we trace out everything except for qubit q. Okay. And the qubit 1 is the one that has the largest length scales, qubit 2 the next, and so on. And so we basically look at this reduced density matrix as a function of q. So that's basically the number of the qubit that we have. And the higher q, the smaller the length scale that it describes. And we see that this very quickly, exponentially quickly, converges to the state plus plus as soon as q becomes larger than some qc, where this qc is the log of pi over lambda. And that means, of course, that as soon as we have a reduced density operator that is pure, it becomes disentangled from the rest. It must do. It can't be entangled with the rest anymore because it's pure. And this plus is nothing but a linear interpolation in the amplitude encoded states. So basically the plus just linearly interpolates between the two neighboring points. And that means that if we move to any q's larger than this qc, all that we do is linear interpolation. We don't need to do anything else. And that, of course, means we can dump those qubits. We don't need them because they only linearly interpolate anyway. And since this, we worked this out for a single sign. And now, of course, for staying with matrix product states, it would not mean anything if we actually then go to a whole Fourier series. But since we here are not wanting to limit ourselves to matrix product states, from linearity, we can now say that this means that any state that has a compact support in Fourier space will have this property. So there is a critical q, a critical number of qubits, that is given by the smallest wavelength that we have in the system. And as soon as we exceed this value qc, all the qubits will just exponentially quickly move towards the state plus and just do linear interpolation. And that means we have something that we call a quantum Shannon-Nyquist theorem that tells us how many qubits do we need for a state, for a function that we would like to realize with a certain minimum wavelength or minimum length scale that we would like to resolve. And of course, the good thing is here, this number of qubits goes logarithmically with 1 over lambda. So we still preserve that exponential advantage over classical computing. We only need a logarithmic number of qubits in order to represent these functions faithfully. Now, let me just give you an example of how this looks like for a Weierstrass function, which is a kind of interesting case because it does show a number of different behaviors. So the Weierstrass function, which is given here, can either be smooth, it can then become fractal, and it can also lose its continuity completely. And this all depends on the values of A that we have here, A and B in these terms here. And so if we look at the I3, this tripartite mutual information that tells us how chaotic the system is. And we here move up in this parameter A, where initially for small a, we have a smooth Weierstrass function. Then it becomes fractal with a Hausdorff dimension that is given up here. And then at a equals 1, it becomes undefined and basically loses all its features, and probably is not going to be ever relevant for physics-like computation. Then we see that this I3 again stays 0 in the smooth region. It does stay 0 in the smooth region if we have enough qubits in our state. And if we use too few qubits, it deviates and starts to become negative. And if we basically choose here a number of qubits that allows us to resolve the Weierstrass function sufficiently, then this I3 stays 0, meaning it is a well-behaved function that we can represent well. And if we under-resolve, then this I3 becomes negative. And the reason for this is seen here, that we basically resolve it fully, and we work out the Fourier transform of our resolved representation of the Weierstrass function in a state. We see this nice kind of spectrum, that compact spectrum. So this is a sparse spectrum. So having a sparse spectrum, having some sparsity somewhere in the system, means that we should expect there not to be any chaos. So we should expect there to be I3 that is close to 0 and certainly not negative. But if we under-resolve with just 16 qubits, then we start seeing aliasing. So basically, we get a whole bunch of terms here in the Fourier spectrum that shouldn't be there, that just arise from aliasing. And that then basically looks like chaos, looks like scrambling has started. So the kind of things that we take away from this is that if we have sufficiently many qubits to represent the functions that we expect to be present in the system fully, then we should get an I3 that is 0 or close to 0, so no scrambling happening. And if then basically scrambling starts to happen, it is because there is some kind of true non-sparsity in that system, and the system really becomes chaotic. The same does not hold if we do under-resolve and not have enough qubits. And here, I just show for completeness, this is basically a plot that shows the various different amplitudes that we need in order to just represent the sign. And what we see here is this limiting QC. And indeed, we see that up to this QC, we do have parameters, an I2 mutual information that is non-zero. Then it drops down to 0 very quickly. And the same here for this I3. So we do see that basically a fully resolved spatial function does have a nice I3 that is close to 0, as long as it doesn't really become chaotic. Now, how do we then utilize this in our computations? Well, the straightforward way to do this is to introduce a quantum regularizer that basically adds to the cost function the value of this I3. So basically, we take this I3 and turn this into a regularizer. And here I show for kind of arbitrary quantum circuit here, with the depth of the quantum circuit, again, this degree of scrambling that we get. Here in black, the trainability. So we do see that the derivatives with respect to the parameters that determine our quantum circuit, trainability is high initially, but then exactly at this edge of chaos goes down to 0. So that means that there is barren plateau happening. And at the same time, this quantum regularizer that we can put in can actually shoot up to avoid getting into this regime here. Okay, and that allows us to basically, yes? Yeah, we add multiple I3s chosen in a nice way. It details too much, but yeah, we need to, so we want to avoid too much overlap between the light cones. And so we add I3s, not just one, but multiple, and the number of, for different partitions of the system. Yeah, but of course, you know, it depends on the problem. It's problem specific what you would add. But yes, essentially that's all that we do. So it's not very difficult to do. It's easy to implement, which is nice. And of course, that can be done in the tensor network computations equally. I mean, that holds for both tensor network computations and others. But what does not hold necessarily is that I3 would only go down to negative values if genuine scrambling happens, because for the tensor networks for the tensor trains, we don't know, at least I don't know, if the same kind of feature is true, that I3 only goes negative if scrambling happens, or whether it might also arise from other imperfections of the tensor train not being able to perfectly realize a function that is not scrambled yet but can't be resolved fully. That's something I don't know. But basically, what we now find with this regularizer is quite an improvement in the optimizations that we do. So, for instance, here we just look at a simple network again that we'd like to optimize. And here we have a pressure field of an isotropic chaotic flow. The cost function is shown here in black without the regularizer and in red with the regularizer. And here the regularizer itself. And what we see here is that if we run these optimization steps with the regularizer, we get in the end a kind of improvement that is roughly 4 orders of magnitude compared to not using this regularizer. And the understanding of that is that because we basically regularize, the initial steps of our optimizer avoid getting into a barren plateau, but essentially kind of intuitively stay close to the valley where the minimum lies. And then at the end here, we switch the regularizer off, just like you do in standard machine learning. So we taper the regularizer. And when we taper the regularizer, it then can find the true minimum. And since it's being close to the actual minimum, it has not gone into any barren plateaus, it will then actually find the true minimum. And in most cases, we find several orders of magnitude improvement over not using this type of regularizer. So this is here for a pressure field, which...
You are trying to describe that pressure field now
by
your set of qubits. Is that the thing that you're trying to do?
Yes, but of course we don't have the qubits, so we do this classically. Of course, we use a quantum circuit that has this shape. It is a rotation, single qubit rotation, then a controlled NOT gate, and that builds these kind of blocks, and that's what we optimize.
And you know that will generate this pattern that you showed that plot? Or?
This generates this pattern, yes. So, I mean, so basically one thing I didn't say is with these, we know that with these kind of quantum circuits, we can generate with the linear depth what is called a alpha design or a T design, people usually call it. So you can, by changing the angles, generate any state that you wish in the linear depth of the circuit. It's just a matter of how accurate this is need to be.
Problem design, you have a specific pattern, you want to find the angles that generate that?
Yes.
That's sort of the goal?
That's the goal. Exactly in the spirit that I had before. So basically what we here have in this, we are still talking about this first part here. So we would like to have variational parameters that can generate us good trial states. So they must be able to generate isotropic turbulence, other kinds of flow fields. And we need to be able to do this in a reasonably shallow circuit, because we don't have very deep circuits.
So operationally, you have a function, a complicated function that's defined. For a tensor that represents that function.
In this case, what we did, yes, but not tensor, but a quantum circuit in this case. You can also do it with tensor. Yeah, right, true, yes. Yeah, but that's what we do, yes.
Yeah, okay.
And the exact gradient or the noisy gradient?
No noise. I'm talking about no noise. You mean noise from the quantum circuit? Yes. No noise.
Because that changes the minimization quite drastically.
Yes, yeah. So that's true, but we don't take that into account. That's something we. if you try to do it with current noise models, you get almost nothing out.
Oh, I'm just even speaking of the fact that you have to repeat the cost function with stochastic bias. Right?
Yes, but okay, so that's true in principle. But then, of course, our point is that, and maybe I should go back here, that we never need and never want to do this. So the idea of this variational algorithms that we have here is to never ever read out the trial function itself. That's completely something we don't want to do, because it's
your cost function. You have the measurement here in two.
Yes.
And so you have to repeat, and then you will have a precision, which will be 1 over the square root of the repetition.
Yes. Yeah.
So you will have noise in your gradient, whatever you do.
True, but we only have a single qubit, so it's far less than for other quantum circuits where you have a huge number of qubits to measure, hence a lot more noise. This is much easier to optimize than anything with multiple qubits, because it's just 1 qubit that you need to optimize. But of course, in principle, yes. Yeah, true. This is not saying this is going to be easy, but basically the idea is that we never want to read out these functions. What we do is, as we here work out the cost function, once we have a solution, we change this circuit to work out the observable that we're interested in. So for instance, we've been working out the observable of lift over drag, and then directly measure that observable, which is again just 1 number. And so that's basically the idea behind this, is that we, in the end, will have to deal with exponentially large types of functions. We don't want to read out their values. All we want to do is work out the observables directly. And we can always do this. We know how to do this from the quantum circuits, the green ones. Okay, but yeah, so basically that's precisely what we did here, to just test whether this works. And we see that it does indeed work, that we get quite good cost functions here for this fluid flow, and here for a Heisenberg model, where we also see a good improvement in the energy, in the ground state energy, of a 1 order of magnitude compared to not using this tapered regularizer. Now, let me just briefly, and I don't have much time left, I guess, say something about that green part and the measurement algorithm. So basically what we do there is, of course, we have to implement complicated evolution steps for partial differential equations, for other types of things. What we do is we write that step that we want to take into a matrix product operator. Then we turn this matrix product operator into a unitary matrix product operator that is conditional upon here measuring some ancilla qubits in state 0. And hence we can realize any kind of evolution or any kind of cost function on that state. And in particular, what we do is we combine all of the different parts of the cost function that we may have, so that indeed the solution is going to be an eigenstate to this operator that we are measuring here, meaning that we have this issue with noise of the ancilla qubit, of course, but we can, in principle, if quantum computers were available, we could actually go towards using quantum phase estimation to improve on that, use amplitude amplification, all of these tricks that people have to read out this one specific qubit more precisely. But that's not something that's currently of interest to us, because we don't have that quantum computer anyway. And so this is typically how such a circuit looks like. We have here a couple of readout parameters that maximize the chances of us succeeding. Here's a linear part of the evolution, here a nonlinear part of the evolution, and everything is just encoded into this single ancilla qubit that we read out and measure. Now, I'm going to show you in the last couple of minutes some examples of what we've been able to do with this setup. Of course, all the examples, I should say that right away, have been done using tensor networks, tensor trains, all those kinds of things. There's nothing in there that's been done on a quantum computer. We did some calculations on a quantum computer in 2019, but since then haven't actually looked at that again. So the first thing is an incompressible Navier-Stokes equation. And there, of course, the reason why we think that our approach is useful is that one needs to resolve length scales from the largest length scale, largest eddies in the flow, which is typically the system size, down to the so-called Kolmogorov length scale. And the Kolmogorov length scale over the largest length scale is what determines the Reynolds number. And the Reynolds number is typically, for things of interest like a Boeing 747, is typically on the order of a couple of millions. And hence the range of length scales that one has to resolve is huge. And that means that classically it's very difficult to actually have enough memory to store these types of flow fields and to process them. And in fact, I think in current CFD computations, the usage or the utilization of the CPU is only roughly around 5%. The rest of the effort is going into memory, kind of memory back and forth. So here having a saving in terms of the amount of memory that is needed, which is exponential, just just in tensor networks helps you a lot in actually making these things faster. And the other interesting thing is that I wouldn't have guessed this a couple of years ago, but the amount of uncertainty in how this fluid dynamics works is huge. So when you look at airfoils that go with these different birds and Boeings and so on, then the estimates that people have on what the lift is over the drag is not just within a couple of percent, it's within an order or two of magnitude. So there is a huge amount of potential for improvement. If you can improve the efficiency of an airplane by just 10%, you're probably going to be, well, one of the richest people on earth. So now let me just say, we kind of writing all of this into matrix product states, solve that equation. And here I show you some results for a jet stream. So that would be basically a stream that comes out of a jet engine. And here we have a fully resolved numerical simulation. And then here for different bond dimensions, the matrix product solutions. And you see that they agree pretty well for reasonably small bond dimensions. And we get excellent accuracy and agreement with the original simulation, even for a compression here of 16:1. So we can basically get away with just a kind of fraction of the parameters needed for a full simulation. Something that we did more recently is the Magnus effect. So there we needed to actually define boundary conditions around the cylinder. And then we look at vortex shedding from this cylinder. So basically you see here vortices forming and being taken away from the cylinder. And basically what happens there is that these vortices are formed with a certain frequency. And we measure this frequency and compare it to the actual numerical results from fully exact solutions. And we find excellent agreement there. And when we look at the computational time using our tensor network methods versus the direct numerical simulation, you see that tensor networks are pretty bad for small systems, but their scaling with the size of the problem, so with the Reynolds number, is much better than the direct numerical simulation. And so for our implementations, but of course where this happens is dependent on what you have, we see here a crossover between the direct numerical simulation time and tensor networks at around the 17 tensors at 17 qubits. And then basically the bigger the system, the better the advantage of the tensor network computations.
How many bits do you require? Do you need to resolve the finest solution?
In this case, 17. In this case, we do 17 per.
Is that enough to resolve the
Yeah.
finest solution?
Yeah, that's enough. So we basically work out the number of bits we need from the Kolmogorov length scale and go down in our resolution to the Kolmogorov length scale, and this is known to be good. And then we start rotating the cylinder. So this is like, you throw a curveball, and we find basically here then this lift then changes. It gets a finite mean value. And here is the agreement with the direct numerical simulations. Again, we get excellent agreement, so we can actually carry out these computations very efficiently using tensor networks. Well, direct numerical simulation is a term that is often used in fluid dynamics to mean to not make any approximations like Reynolds averaging or large eddy simulations or any other closures for the turbulence models. So basically, you take the Navier-Stokes equation, solve it numerically exactly without making approximations.
Using what method?
Sorry?
Using what method?
Oh, no, you can use still time-stepping methods. You can still use what you want. But you can't basically simplify the equation to a kind of simpler version of the Navier-Stokes equation. Here we've done some combustive flows. Sorry, I need to get on. Just combustive flows, where we basically look at combustive flow between here, basically one component, the other component, then they start combusting. And that's basically what would happen in a jet engine. And we can, on a laptop, easily solve grid sizes of 128 to the power of 5. This is not so easy to do classically on a computer. Again, the agreement is very good. And I'm just going to show you one last thing. And this is really about convection. So this is typically how these simulations look like. Here we have a hot plate at the top, a cold plate at the bottom. And what then happens is that this thing starts to oscillate and transport heat, not just by conduction, but also by convection. And this is a question here that's not been resolved. How does the energy transport, the heat transport, change with what is called the Rayleigh number here? At around 10 to the 12, some papers predicted a change in this behavior from this kind of line towards a constant. And then there are some comments that say, well, this is actually not true. This is not what should happen. And resolving this question here, what happens up there at these large Rayleigh numbers, is really not a solved question. And calculations that were carried out in 2011, 2012 here needed around a year to calculate these values here on a big computer. So they really run for a long time. And we can now go up to here in a day or so. So this actually does allow us to do some of these calculations more efficiently than we think other people can do. And of course, we get very good results here that agree very well with the literature. Now, let me come to an end and just thank the people we're working with, particularly our EU project QCFT, where we actually do a large part of this work, the group members from that project. And we've been working with Payman Gibi from Pittsburgh, who is a rocket scientist, I would say. So he is doing these jet engines with NASA. Nick, who has been my PhD student, is now an electricity trader. Steve Pope, who has been working on some of this, and Michael Lubash, who is now with Continuum in London. Okay, thanks you very much.
Hi. Oh, thank you very much for a very interesting talk. In one of your slides, you showed formula which I recognize as QTT format.
In which slide?
It's a bit hard to say, but it was towards the beginning. So before the applications, really, one of the first slides.
Oh, the first slides.
Yeah, maybe. Yeah. 2 slides later, and one more later.
Yeah.
And yeah, this one. Yeah, this one. So, and maybe I misunderstood. Maybe can we go on the next slide? I'm sorry. I'm so this formula here resembles what I think is QTT format, but you use slightly different name. And on a previous slide, you had a reference to Penrose paper.
Yeah.
So I'm wondering if there is a connection, if we should use a different name for this, if there is an earlier reference, why you chose to call it amplitude encoding rather than QTT format?
I mean, I think in quantum machine learning, people call it amplitude encoding. There's amplitude encoding, there's base encoding, different encoding. So I just chose that name, which I think was introduced, if I'm not mistaken, but correct me if I'm wrong, by the quantum machine learning guys, and in particular probably by Maria Schult. So she introduced this name. It's not my invention.
I think the idea is implicit in like the quantum Fourier transform around.
Right, exactly. Yeah, but it was probably not called amplitude encoding. So yeah, it's also in quantum Fourier transforms. Absolutely right. Yeah. So it's a very kind of standard thing. It has probably a ton of names.
And the Penrose reference is related to.
Oh, the Penrose reference. I think that's interesting. So actually, Penrose in 1971 wrote in what I think is the first paper on the graphical notation of tensor networks. So he wrote this paper where you see for the first time kind of joining 2 legs is contracting, and he had upper legs and lower legs, and they basically did that. I think there's nobody who'd done this before, but it was part of his PhD, and then in 1971 he wrote this paper. But yeah, it's nothing. He didn't do any numerics or anything like that. Yeah.
Hi, I wanted to ask about the slide where you're looking at the sine function and sort of, it was right before the Weierstrass function, trying to understand sort of some complexity statements. So this, what's lambda exactly?
Lambda is the wavelength of the sine.
Okay, so this is a single sine.
Yeah.
So I mean, you're trying to get some estimate of kind of what functions QTT can encode and how efficiently.
Yeah.
What's kind of the statement of what's the final statement of like the class of functions that you're concluding?
So,
and how does it not violate the normal Nyquist-Shannon theorem?
The normal what?
The normal Nyquist-Shannon theorem. I mean,
it doesn't violate that at all. The Nyquist theorem also says you have to basically sample the function at every half of the wavelength. Here it's just a factor of pi, so it's a little bit worse, so it doesn't violate it, it's a bit worse than that. And basically, it doesn't violate it at all, but what actually is not, it's not obvious that it does the same thing, that you can get the same number of qubits and get away with that. But basically what the exact statement is that if you have a function that is represented on a compact part of the Fourier spectrum of k values, you take the maximum k value as your 1 over lambda here, and that basically determines the number of qubits you need. And anything beyond that is just linear interpolation. It doesn't give you any aliasing or anything like that.
So if I exponentiate both sides, I sort of get back the Nyquist theorem, basically.
Yeah, except for a factor of
except for a vector.
Yeah, except for a vector.
Thank you.
But it doesn't violate anything. Yeah, no, that's true.
I am terribly sorry. I have to cut out the rest of the questions.